Have you ever felt like you were on the verge of witnessing something so revolutionary it would forever split history into a before and an after? What if I told you that moment isn't in the distant future, but is happening right now, in labs colder than deep space, where scientists are teaching the very atoms of reality to think? We stand at the dawn of the quantum age, a period so transformative it will make the digital revolution look like a quaint relic of the past. This isn't just about faster computers. It's about fundamentally rewriting our relationship with the universe itself. So, buckle up, because today we are peeling back the curtain on a technology that will change everything you thought you knew about medicine, finance, security, and even the nature of reality. Our story begins not with a rocket launch, but with a silent, earth-shattering calculation. In a world-first global banking giant, HSBC partnered with the pioneering minds at IBM. Their goal was audacious: to use a quantum processor to peer into the chaotic, unpredictable future of the bond market. The result? They improved their ability to predict bond trades by an astonishing 34%. Now, 34% might sound like a respectable number in a school exam, but in the high-stakes world of finance, it's a seismic event. We're talking about a domain where experts spend billions to gain a fraction of a percentage point of an edge. To achieve a 34% leap is like a horse-drawn cart suddenly breaking the sound barrier. Experts didn't just call this a success, they called it a Sputnik moment for quantum technology. Let's pause and truly understand that phrase. In 1957, the Soviet Union launched a small beeping satellite named Sputnik into orbit. On its own, it did very little, but its existence sent a shockwave across the globe. It was a clear, undeniable signal that a new era had begun, the space age. It ignited a fire of competition, innovation, and ambition that ultimately put a man on the moon. This HSBC IBM achievement is our modern-day Sputnik. It's a tangible, real-world demonstration that quantum computing is no longer a theoretical physicist's daydream. It has left the blackboard and entered the boardroom, symbolizing the dawn of an entirely new computing era. It's the first note in a symphony that will redefine our world. When a technology promises to change the world, the first question on many people's minds is, where's the money? The consulting firm McKinsey & Company, a group paid to make precise, calculated predictions, has projected that quantum computing could unlock an almost incomprehensible $1.3 trillion in value by the year 2035. To put that number in perspective, it's larger than the entire economy of many developed nations. And here's the most telling detail. McKinsey predicts that more than half of that value, over $700 billion, will come from financial services alone. Why finance? Because modern finance is a world built on fantastically complex mathematical models. Banks and investment firms are constantly trying to optimize, to find the single best answer among a near infinite number of possibilities. Think about a bank managing its investment portfolio. They have thousands of assets to choose from, each with its own risk, potential return, and correlation to every other asset. The number of possible combinations is astronomical, far exceeding the capabilities of even the most powerful supercomputers today. Classical computers have to take shortcuts. They have to make approximations and educated guesses. But quantum computers don't guess. They are designed to explore every single possibility simultaneously. This power to navigate infinite complexity is why banks are so captivated. They see a future where they can optimize trading strategies with perfect accuracy, detect fraudulent transactions in real time before they happen, and assess market risk with a clarity that is currently impossible. HSBC's breakthrough wasn't just a successful experiment, it was the first taste of a trillion-dollar feast. This revolution didn't appear out of thin air. Its roots stretch back to the 1980s, a time of big hair, neon colors, and groundbreaking physics. It was during this decade that three brilliant minds, John Clark, Michel Dvoret, and John Martinis, conducted research that seemed at the time to be purely academic. They were working in the strange and wonderful world of quantum physics, exploring the bizarre rules that govern the universe at the subatomic level. Their work focused on creating and controlling tiny electrical circuits that behaved according to these quantum rules. In doing so, they achieved something monumental. They built a bridge between the ethereal, probabilistic world of quantum physics and the solid, tangible world of silicon chip technology. This was the crucial link, the Rosetta Stone, that would allow us to translate the laws of the universe into the language of computation. Their research, which ultimately earned them the Nobel Prize in Physics, laid the foundational groundwork upon which every modern quantum computer is built. They are the quiet architects of our new era, the pioneers who dared to believe that the weirdness of the quantum realm could be harnessed to solve humanity's biggest problems. Without their foundational work, the quantum dream would have remained just that, a dream. We are now entering what many believe will be the single most transformative period in human history. For all our technological progress, our computers, from your smartphone to the largest supercomputers, are still fundamentally just sophisticated abacuses. They work with bits, which are simple on or off switches, representing either a 1 or a 0. But quantum computers represent a complete paradigm shift. They don't compute with switches. They compute using the building blocks of matter itself, atoms and the subatomic particles within them. Think about that for a moment. We are learning to speak the universe's native language. This incredible power is why quantum computing has drawn the intense, watchful eye of global intelligence agencies. The backbone of our modern digital world, from our bank accounts to our national secrets, is protected by encryption. This encryption relies on mathematical problems that are so complex they would take a classical computer billions of years to solve. But for a mature quantum computer, breaking this encryption could be as simple as a hot knife through butter. The very power that can unlock the secrets of nature can also unlock our most closely guarded secrets. This creates a high-stakes race, a silent, global competition to develop quantum capabilities, and just as importantly, to develop new forms of quantum-safe encryption before our current digital walls come crumbling down. While the threat to cybersecurity is real and immediate, it is only a sliver of the quantum story. To focus solely on encryption would be like looking at the invention of the printing press and only seeing its potential to forge documents. The true promise of quantum computing stretches far beyond security, holding the potential to revolutionize every major field of human endeavor on a global scale. Imagine a world where we can design life-saving medicines not through slow, expensive trial and error, but by simulating the exact interaction of a drug molecule with a virus at the atomic level. We could create personalized treatments for diseases like cancer and Alzheimer's with unprecedented speed and accuracy. Think about our planet's energy crisis. Quantum computers could help us unlock the holy grail of clean energy, nuclear fusion. By perfectly simulating the conditions inside a star, we could design a reactor that provides virtually limitless, zero-carbon power. Or, on a smaller scale, we could design ultra-efficient batteries and revolutionary new materials for solar panels, completely transforming our energy grid. From material science, where we could invent room-temperature superconductors that would eliminate energy loss, to artificial intelligence, where we could train models of unimaginable complexity, quantum computing offers a key to unlock humanity's greatest scientific challenges. It's not just a new tool, it's a new way of seeing and interacting with the world. To understand how this is all possible, we have to take a short trip into the bizarre and wonderful realm of quantum mechanics. For centuries, our understanding of the universe was governed by classical physics, the physics of Isaac Newton. It's a world of certainty and predictability. If you throw a ball, you can calculate its exact trajectory, speed, and landing point. Everything is deterministic. But in the early 20th century, scientists discovered that when you zoom down to the level of atoms and particles, these comforting rules break down completely. This is the world of quantum mechanics, and it operates on a foundation of unpredictability and probability. A quantum particle, like an electron, doesn't have a single, fixed position until you measure it. Instead, it exists in a cloud of possibilities, a state of superposition. It's in all possible places at once. It's a concept so strange that it baffled even Albert Einstein, who famously disliked its inherent randomness. But it's this very unpredictability, this embrace of probability over certainty, that quantum computers harness as their greatest strength. They don't just calculate one answer, they explore every possible answer simultaneously. So how do you build a computer that thinks in probabilities? It requires some of the most extreme engineering on Earth. Inside a quantum computer, you'll find a chandelier-like structure of gold and copper, where chips are cooled to temperatures near absolute zero, 100 times colder than the coldest reaches of outer space. This extreme cold is necessary to create a perfectly controlled environment, isolated from any external vibration, heat, or radiation, which could disturb the delicate quantum states of the particles inside. At the heart of this machine are the qubits. While a classical bit can only be a 0 or a 1, a qubit, thanks to the principle of superposition, can be both a 0 and a 1 at the same time. Think of it like this. A classical bit is a light switch. It's either on or it's off. A qubit is like a dimmer switch, able to exist in any state in between. But a better analogy is a spinning coin. While it's spinning, it's neither heads nor tails. It's a blend of both possibilities. Only when you stop it, or measure it, does it collapse into one definite state. Now, imagine you have two qubits. A classical computer would need 2 bits to represent one of 4 possible combinations, 0, 0, 0, 0, 1, 10, or 11, and it could only work on one combination at a time. But 2 qubits can represent all 4 of those combinations simultaneously. With 3 qubits, you can represent 8 combinations. With 300 qubits, you can represent more combinations than there are atoms in the known universe. This is the source of quantum's exponential computational power. It's a parallel processor on a cosmic scale. This ability to process countless probabilities at once is what allows quantum computers to do something truly profound: simulate nature itself. This was an idea first envisioned by the brilliant and eccentric physicist Richard Feynman back in the 1980s. Feynman understood that the universe is fundamentally quantum. He argued that if we ever wanted to truly understand reality, from the behavior of molecules to the formation of galaxies, we could not do it with classical computers. Trying to simulate a quantum system with a classical computer is like trying to describe a beautiful symphony using only the words loud and quiet. You'll miss all the nuance, harmony, and complexity. Feynman prophesied that to understand a quantum world, we would need a quantum computer. He saw it as the key to unlocking reality's source code. Because qubits operate by the same strange rules as the rest of the universe, they can model it with perfect fidelity. This accelerates scientific discovery in ways we can barely comprehend. We can test new theories in physics, simulate chemical reactions that are too dangerous or expensive to perform in a lab, and explore the fundamental nature of reality in a way that was previously confined to the realm of science fiction. Quantum computing isn't just about finding answers. It's about asking entirely new questions. If this technology is so powerful, why don't we all have quantum laptops yet? The answer lies in one of the biggest challenges in all of modern science: decoherence. Building a stable quantum computer is extraordinarily difficult because the quantum state is incredibly fragile. Decoherence is the tendency of a qubit to lose its quantum properties and fall out of alignment at the slightest disturbance. Imagine trying to keep thousands of spinning coins perfectly synchronized on the deck of a ship during a violent storm. The tiniest vibration, a subtle change in temperature, or a stray magnetic field can cause a qubit to decohere and collapse into a boring old classical bit, destroying the computation. This is why quantum machines must be kept in those hyper-controlled environments, shielded from the outside world, and cooled to temperatures colder than space. Preventing decoherence is the central engineering problem of the quantum age. The race to build a powerful quantum computer isn't just about adding more qubits. It's about making those qubits more stable and resilient, so they can perform complex calculations before this quantum ghost disrupts the machine. This immense challenge has not deterred the world's technological giants. A new global race has begun, a 21st century equivalent of the space race, with 4 titans leading the charge: IBM, Microsoft, Google, and Amazon. Each of these companies is pouring billions of dollars into research and development, and each is pursuing its own unique strategy, hitting different milestones, and guided by a distinct long-term vision. This isn't just a competition for market share. It's a race for the future of computing itself. IBM, a legacy powerhouse in computing, has been a pioneer in the quantum field for decades. They have a clear, publicly stated roadmap. Their near-term goal is to achieve what they call quantum advantage by 2026. This is the point where a quantum computer can solve a real-world, commercially relevant problem better, faster, or cheaper than any existing classical supercomputer. They aren't waiting for a perfect million-qubit machine. They're focused on finding practical applications for the powerful, albeit noisy machines they have today. Their Heron and Nighthawk chips are already pushing the limits of performance, and their upcoming Starling and Blue Jay systems promise massive leaps in scale and operational capability. IBM's ultimate vision is a large-scale, reliable, and fault-tolerant system by 2029, a machine that could truly begin to tackle humanity's grand challenges. Microsoft has been playing the long game, taking a path that is both incredibly ambitious and fundamentally different from its rivals. After 17 years of deep, often secretive research, they announced a monumental breakthrough: the creation of a particle that was once thought to be purely theoretical. This particle is the basis for their topological qubits. The science is incredibly complex, but the implications are revolutionary. Unlike other types of qubits, which are notoriously fragile, topological qubits are inherently stable. Their quantum information is protected by the very structure of the particle, making them far more resistant to the dreaded problem of decoherence. These qubits are also incredibly small and scalable. Microsoft's vision isn't just a room-sized supercomputer. Their groundbreaking approach could one day pave the way for powerful, handheld quantum processors. It's a high-risk, high-reward strategy that, if successful, could leapfrog the competition entirely. Google grabbed headlines around the world in 2019 when its Sycamore chip became the first to achieve coincidental quantum supremacy. This is a specific academic milestone where a quantum processor performs a calculation that would be practically impossible for even the most powerful classical supercomputer. The task itself was esoteric and had no immediate practical use, but it was a powerful proof of concept, a hello world moment for the quantum era. But Google didn't stop there. Its successor, the Willow chip, has already surpassed expectations, demonstrating 5 times longer coherence, the amount of time a qubit can hold its quantum state, and record-breaking speed. Google claims Willow can perform calculations that would take the world's fastest supercomputers longer than the current age of the universe. They are relentlessly focused on scaling up and improving the quality of their qubits, aiming to turn their demonstrated supremacy into practical, real-world advantage. Amazon entered the quantum hardware race a bit later than the others, but they brought their signature pragmatic and customer-focused approach. Through their Amazon Web Services, AWS cloud platform, their primary goal is integration and accessibility. They are focused on building a quantum ecosystem and making various quantum processors available to researchers and businesses today. Their own in-house processor, Ocalot, is based on a novel design using cat qubits, which have a unique built-in error correction mechanism. This design has been shown to reduce the overhead needed for error correction by a staggering 90%. A huge step toward building more practical and reliable systems. Amazon's strategy is to democratize access, moving toward a future of quantum as a service, where enterprises worldwide can tap into the power of quantum computing through the cloud, without having to build their own multi-million-dollar cryogenic labs. Let's bring this back down to earth. What does this mean for our daily lives? We've already seen the impact in finance with HSBC's success. Quantum's ability to process a near-limitless number of scenarios at once gives banks a crystal ball for assessing risk, detecting sophisticated fraud rings in real time, and optimizing trillions of dollars in global trade. It's a level of financial insight and accuracy that was previously unimaginable, but the impact on medicine and energy will be even more profound. Today, discovering a new drug is a decade-long, billion-dollar process of trial and error. With quantum computers, we can simulate molecular interactions with perfect precision. Scientists could design a drug that binds perfectly to a virus, disabling it completely, or create a personalized cancer therapy based on the unique genetic makeup of a patient's tumor. We could design new catalysts to pull carbon out of the atmosphere, or create new materials for ultra-efficient batteries that could power a car for 1,000 miles on a single charge. We are talking about solving some of the most fundamental and pressing challenges facing humanity. As if quantum computing weren't transformative enough, its true power may be realized when it's combined with another revolutionary technology: artificial intelligence. AI, particularly machine learning, is all about finding patterns in vast amounts of data. The more data, and the more complex the model, the more powerful the AI becomes. The problem is that training today's most advanced AI models already pushes the limits of our computational resources. Quantum computing shatters those limits. It can accelerate AI by exponentially boosting data processing and model training capabilities. This creates a powerful feedback loop. Quantum computing makes AI smarter, and that smarter AI can then be used to help us design better quantum computers. This synergy will fuel the next wave of intelligent systems, creating AI that is not just smart, but perhaps truly wise. This incredible power brings us back to the security paradox. Quantum computing is a double-edged sword. It threatens to break the very encryption that underpins our secure digital society. However, it also offers the solution. The same principles of quantum mechanics that allow for code breaking also enable the creation of quantum-safe security. Technologies like quantum key distribution, QKD, use the laws of physics to create encryption keys that are theoretically unhackable. If an eavesdropper tries to intercept the key, the very act of observing it disturbs its quantum state, immediately alerting the sender and receiver. This creates a new frontier in digital protection, and global agencies are in a desperate race to develop and deploy these quantum-safe methods before large-scale code-breaking quantum computers become a reality. The impact of this technology will ripple through every corner of our economy, from logistics and manufacturing, where quantum computers can solve impossibly complex optimization problems to create hyper-efficient supply chains, to urban planning, where they could design traffic flows that eliminate gridlock entirely. Every industry that relies on optimization, simulation, or data analysis will be transformed. The market for quantum computing is projected to reach an incredible $173 billion by 2040, reshaping our industrial landscape and creating entirely new economic sectors. This isn't just another technological upgrade, it's a fundamental economic shift. So, when does this future arrive? That is the billion-dollar question, and the experts disagree. The CEO of NVIDIA predicts it will take 15 to 30 years for the technology to fully mature. Google is more optimistic, suggesting a timeline of 5 to 10 years for commercially useful machines. IBM has set a target of 2033 for a truly large-scale system. The truth is, we are still in the early days. Current systems operate with tens or hundreds of qubits. The full-scale deployment needed for things like breaking encryption or designing complex molecules will likely require machines with millions of high-quality stable qubits. The race is a marathon, not a sprint. But what's undeniable is that progress is accelerating at a breathtaking pace. Every month brings new breakthroughs that were thought to be years away. This technological race has inevitably become a geopolitical one. Quantum capability is now seen as a matter of national security and economic competitiveness, sparking an intense rivalry, particularly between the United States and China. Both nations are investing billions of dollars in public and private funding to lead the world in this critical field. The country that masters quantum computing will hold a significant advantage economically, technologically, and militarily. It has become one of an elite few scientific frontiers that will define the power dynamics of the 21st century. Despite the challenges and the uncertain timeline, the groundwork for this new world is being laid today. The first quantum computers are running, the first real-world problems are being solved, and a global community of brilliant minds is dedicated to overcoming the immense hurdles that remain. When this technology finally matures, it will do more than just give us faster computers. It will fundamentally redefine how we think, how we solve problems, and how we interact with the fabric of nature itself. It will give us a tool to understand the universe in its own language. We are living through the dawn of the quantum age. The lesson here is one of profound optimism and a call for curiosity. Throughout history, humanity's greatest leaps have come from our willingness to embrace ideas that seem strange, counterintuitive, and even impossible. Quantum mechanics is the ultimate example of this. By daring to explore a reality that defies our everyday senses, we are on the verge of unlocking capabilities that will empower us to solve our biggest problems. The advice for our daily lives is to cultivate a quantum mindset. Embrace uncertainty, stay curious, and be a lifelong learner. The world is changing faster than ever, and the ability to adapt and learn will be our most valuable asset. This journey is just beginning, and it raises so many fascinating questions. What problem would you want to solve first with a powerful quantum computer? And how do we ensure that this incredible technology is used for the benefit of all humanity? I'd love to hear your thoughts in the comments below. Thank you for joining me on this incredible journey to the edge of reality. I wish you all the very best of health and a future filled with wonder. If you enjoyed this deep dive and want to stay ahead of the curve on the technologies shaping our world, please consider subscribing to the channel. We have so much more to explore together.